Good morning. It's actually nice to speak in a small family atmosphere of people still fighting their hangovers. When I saw the turnout this morning, I was thinking there must have been a conference banquet last night, right? And I looked at the program and it was not wrong. So time to re-sing. So what's with that re-sing, right? I looked at some of the previous semantic web conferences. I certainly am not the first one to give a talk on the intersections with machine learning and how these fields relate and so on. The last talk that I've seen was by Marko Grobelnik about 6 years ago, so that gives me a chance to give you an update on what has been happening recently. So that's one of the points where I differ. And the other point where I wanted to be different from the previous machine learning speakers can be somehow expressed by the phrase that actually paraphrases JFK, right? Ask not what machine learning can do for you, ask what you can do for machine learning. So that is to say, the previous talks were looking mostly into how you guys can use our algorithms for your purposes, like ontology populations. I will review a few of these points. And I'll be mostly looking into the other direction, that is to say, how what you produce, that is ontologies, knowledge bases, all the semantic web stuff, can be made available or understandable for our purposes, for machine learning, as an input for learning. Now, for those of you who have pretty much no idea what machine learning is, or very little idea, I'll quickly go through an intuitive introduction. So, at this first approximation, we have a machine that learns, and learning means it observes something and improves. So observing something means we have some base of data on the left-hand side, and we produce what we call knowledge. So what is the difference? I mean, I don't want to become philosophical here, but data for me is something ground. It's ground observations, which do not allow you to make any inference steps per se. It's just the fact. Whereas knowledge has the form of different patterns, which allow you to perform inference steps. So that is to say, infer new data from existing data, or even new knowledge from old knowledge. So that is the difference, although a little bit circular, right? Knowledge allows you to infer knowledge. Okay, you could argue. But anyway, so this is the usual way that we present the inputs to machine learning. So that has very little to do with the way or with the standards you are used to, the advanced knowledge and data encoding standards. What we usually expect is a matrix or a table in which each row is or represents a data sample, which usually are assumed to be sampled independently from each other, but let's not become statistical today. And the columns, they represent attributes. So each datum, each sample, is a tuple of attribute values. So this is going to be somehow significant when we talk about combining learning with the semantic web. Now, if we look at the right-hand side, at the knowledge produced by learning algorithms, these are some examples of what such a knowledge usually looks like as produced by a machine learning algorithm. Again, not in the form that you would be, let's say, conductive to. So, quickly, let's just sample from these diagrams. So this is a decision tree. There are algorithms that can look at data and produce a structure like this. So what does this structure tell you? So if you want to predict one quantity, let's say one of the columns, which we saw, from the other columns, So this is a prescription on how to do it. So you test the values in the attributes which you know, and according to the test you are swayed one or the other way until you arrive to the prediction of the attribute that you don't know. Okay? So that is a thing that a machine learning algorithm can produce. This is just a slight difference of what we've seen. If you take these rules, which are implicit in the path, and rewrite them into explicit rules, you have what's called a rule set. And also there are algorithms that produce exactly this, rather than the decision trees. Now, you have definitely heard of neural networks. So that's another way of expressing a pattern. It's not explicit, it's not readable, but it's still there. The pattern is in the form that if you put some input values to the input units of the network, through all this processing, you arrive at the output values. And there are, again, algorithms which can adapt the function that is implemented by the network according to data that you have, so that the network fits the data. Again, that's an example of machine learning. Okay, let's just mention that this picture is from a machine learning strategy that was very popular about 10 to 15 years ago. It was called, or it's still called, support vector machines. And I'm mentioning it because it will be significant, one of the possible applications of the learning in semantic web. Briefly said, what the algorithm does is that it tries to separate data instances in one class. Again, the class will be indicated by that one selected attribute, one selected column, from the other class, and does it in such a way that it maximizes this gap, this margin between the classes. And the classifier itself is actually this line, or this mathematical prescription, which tells you when my new instance arrives, whenever it falls on top or above the line, I'm going to classify it as red, otherwise blue. Okay, so that's another way of classification. And I also included a picture which shows something that has nothing to do with classification, just to prevent the feeling that all we do in learning is learning to classify. So this also is a tree, just like this, but the resemblance is only shallow. This is what's called hierarchical clustering. So here your data comes without any information about classes, and your algorithm actually looks for a natural splitting of your instances into what can be called new or invented classes. It doesn't matter what these abbreviations really mean, but these were identified to be sets of instances which are different from each other, but similar in each cluster. And the tree actually captures the similarities between the individual clusters and between the clusters of clusters. So what you get is like a phylogenetic tree as known from biology. Okay, so this was a quick sample of some typical machine learning algorithms. Now, what could be the possible connections with the semantic web? So obviously there are two basic ways to look at it. This is one of them. So this is the scenario that I'm not so much going to talk about, in which a machine learning algorithm, using some observations or data, produces something for the purposes of building a knowledge base or a semantic web structure, let's say. So lots of research has been conducted along this direction, pertaining, for example, to learning concept taxonomies through hierarchical clustering. So remember the last example I gave here. Doesn't this somehow remind you of a sort of a taxonomy? Of course, getting a hierarchical clustering can be a good basis for forming a taxonomy of concepts in which each cluster and clusters of clusters would represent the concepts, right? So this is certainly an idea that has been exploited in lots of research. I suppose you've heard of works that learn deep annotation rules. So one task that I imagine is rather frequent in what you do is to populate concepts, right? Which can be done by parsing textual sources and finding the occurrences of concept individuals, concept instances. Now, you can do it manually, or you can have an algorithm learn how to do that. So this is also one of the, let's say, prestigious tasks in which machine learning was applied. Also, tasks such as ontology alignment and duplicate detection were in the scope of machine learning research before. So once again, all this stuff was covered many times by machine learning speakers at Semantic Web venues, and I'm not going to reiterate on that very much. What I'm going to look at is the reverse relationship in which from a knowledge base such as that, or such as one produced by Semantic Web Standards, act as an input to machine learning. So in the previous schema, I showed you data goes to machine learning. Well, okay, if we add a prior knowledge, then perhaps it could be relevant enough so that the learning from data could be made smarter or more effective. Or there are even scenarios in which you would learn only from knowledge, so from rules, from concepts, to induce new knowledge. So there is recently lots of motivation for thinking about these scenarios. This is mainly because of the rise of very large and sometimes even reliable, curated knowledge bases, such as the free-based DBpedia, the Google Knowledge Graph, which is like, I don't know, like 40 million relations. I don't know if you told me billion, I would believe you. I don't remember the numbers, but it's big. So why don't we use that for better learning? So the answer to this question is because the current learning algorithms are not exactly ready for that. And I will now review how exactly ready they are. So what, in my view, the state of the art of digesting such advanced databases with machine learning is. I promised in the beginning that I would talk about new things, but my heart would not let me not mention the field that where it all started on day 0 of relational learning, and this is a family of methods, or even a research field called inductive logic programming. So I'm presenting it with boxes just like I presented usual machine learning, and the boxes, the previous diagram is actually subsumed. So we again have data going into this magical ILP box, and we have knowledge. But what's different is that we have another input called background knowledge. So that is to say, inductive logic programming, ILP, methods are those machine learning algorithms are one of those which can, beyond data, also take account or respect existing prior knowledge. So how does this technically work? Of course, I'm not going to spend this lecture on the theory of ILP, but at least to give you the intuition behind it. So first, technically speaking, these entities, knowledge and data, they take the form of theories in first-order logic. Usually not the whole expressiveness of first-order logic is indeed used. We often resort to data log or other subsets of first-order logic, but in general, it is a first-order logic theory. So that's a powerful weapon, right? And then we have data. They usually take the form of logical ground facts. So it's not difficult to rewrite a table such as that we've seen before into a set of ground facts. So that's not a limitation for the whole learning endeavor. And on the output, we have this new knowledge and logically, or well, naturally, it's also a first-order logic theory. Okay, so this is maybe not very explanatory, but I'll give you an example which looks scary. It doesn't look anything like semantic web. It looks like chemistry, but don't worry. We don't need to study molecules. This is just to illustrate a specific task in which the scenario was applied. So here we had a bunch of molecules, and about some of them we know they are mutagenic and the others are not. These are the data, right? And they have their classes, that is the mutagenicity or not. And we want to have the algorithm learn from the descriptions of the molecules to classify new molecules whether they are toxic or not. Okay, so it's a very natural task. The problem is that molecules are structures. How on earth are you going to encode a molecule into a tuple in a matrix? Right? You have practically no way of doing that reasonably. But in the logical world, the language does allow you to express such structured data. So what you would do with the ground fact, you would just indicate about these constants whether they are mutagenic or not. So that's the instances and classes. But the whole knowledge which describes the structure and properties of those molecules, that's hidden in the theory here. So here we say that in the first drug we have something we call C1, and it's an atom of type carbon. Okay. Are you people familiar with these notations of logical facts? I mean, that's not so different, you know, data log and semantic web. It should be pretty much related, okay? But we also say that there is a double bond in the drug between some two atoms, one of them described here. And we also define some concept. So what we can have in the background knowledge is also rules, not just the ground descriptions, but also rules that define concepts. Okay, so we say in this drug, now it can be any drug because we start here with a capital letter, which means it's a variable. Okay, I think in your community you use question marks, right, for variables. So here in Prolog we use capital letters. Now get used to it. So in any drug, there is an anthracene structure, you know, God knows what that is, if there are two rings out of which both are benzene rings. That I vaguely remember from high school what benzene rings are. Okay. So this is the way that we describe the learning task. And indeed, there is a thing called ILP, which obviously I cannot give you the full account of, which is able to digest it and produce a theory that correctly classifies these examples. So that could be, I mean, if you're a chemist or biologist, you would probably kill me. This is nonsense. But in principle, you can induce rules such as mutagenic drug. So any drug is mutagenic if it contains a benzene ring connected with a double bond to a molecule which is just existentially quantified. So any molecule. Okay, so this is how ILP sort of works from the outer view. Now, very quickly, how is that done? You know, what is done in this box that you can induce logical rules like this? By the way, why it's called programming? It's because this rule is actually a clause in the language of Prolog. And Prolog happens to be a programming language, right? So with full-blown fantasy, you could imagine that you could even induce logical programs with recursion and functors, right? That is undecidable and, so on. So let's not talk about programming anymore, just to explain why we have the name here. But again, back to the question, what's done in this box? As you could expect, you know, as in AI, practically everywhere in AI, the problem is reduced into search, into combinatorial search. And where you search? Well, you search in an abstract space of such possible rules, right? And the space is organized. So we have a lattice, actually, in which each arrow means this thing is more general than this thing. So this will be true for more drugs than this, because we have some condition here. And the nice thing about the language of, well, let's say data lock, to stay close to the earth, is that this lattice of generality can be well defined and computed. There are some problems, but in principle this is possible. So we know that, for example, if we are covering too many negatives, non-mutagenic drugs with this rule, which we would be, we have to specialize. So we have to go down this lattice. Whether we go this way or this way, that's a matter of heuristics. How many examples are covered here and so on, until you arrive to something that is true, or at least it looks true on your data. Okay. Usually these lattices are very huge, so this is a understatement. But so that's how ILP works. So, in my opinion, this was the first framework that really can account for input, background knowledge, and that in principle can be, let's say, an RDF store or so. So this field has been under quite energetic research since the 90s. Now it's slowing down, but still alive. Mainly in Europe. The Americans don't like ILP so much. Okay, let's not get deep into this discussion. I say we because I'm part of the community. So we hold annual conferences of, let's say, 50 people each year. In ILP 2008, which was in Prague, we had Frank Harmelen as the invited speaker. I understand Frank is one of the well-known researchers in the semantic web. Nowadays, the focus is mostly on combining the logical underpinnings with probabilistic inference. So what is now more in fashion in Europe is a field called probabilistic ILP, where people, they put probabilities to these clauses and they infer how the conclusions are probable if the observations have these various levels of probability and so on. And actually the Americans are approaching it from the other end, so they call it statistical relation learning. So they have their statistical models like Bayes nets and whatever you want, you name it. And then they include some logical pieces in the framework to account for, let's say, structure of input data. Then the field would be called statistical relation learning. That is also, let's say, a keyword that has been quite popular in the last years in the machine learning community. Now, the main issues of the framework of ILP for real-life application is scalability. It has always been a problem, it's still a problem, scalability, for big data and big knowledge bases. So, especially now that we're talking of Google Knowledge Graph and these beasts that are gigantic, applying ILP algorithms as they are, in their general form to such large databases would be, a Sisyphus work. So you would not scale. You could not do reasonable experiments, frankly. So you would have to sample a lot, subsample data a lot. Of course, the reason why we care about probabilistic ILP is that the logical framework doesn't really capture uncertainty and numerical reasoning and so on. What is specifically an issue for this talk is I have been talking about data lock and first order logic, but that's not exactly the standards that you use, right? Like you are more, the semantic web is more about the description logics and frameworks like this. So what I want to look into is how people now have adapted the ILP framework to deal with these standards. So there is a nice well, first of all, there are not many people doing this. To my best knowledge, there are two groups. One is in Germany, and these people are, I don't even know them, John Lehman, and there is another guy, Hellman, who published an, I think, called DL Learner. And can you raise your hands, anybody who has heard of DL Learner? Oh, perfect. I thought that would be, yeah. So that is a machine learning algorithms which, as an ILP, induces concept descriptions from examples. In this case, it's concept descriptions in the ALDL. Can I say ALDL language? Okay, just don't, I'll make sure that people don't crucify me if I say something, I'm not a semantic web researcher, I'm a machine learning researcher, so allow some, glitches. In this language, okay, so the principle is pretty much the same as in ILP, so you search a subsumption lattice, which is somewhat more manageable in the case of description logic. So I'm not drawing the whole graph, but one example that's actually given in the Lehman's paper in the Journal of Machine Learning Research was one which goes bottom up, so from the general to the specific, and guided by the arriving examples. So it finds that all the examples were actually persons, so it specializes the universal concept into the person concept, and gradually it arrives at the correct description, which covers all positive examples and leaves out all the negatives, and which says that all the positive examples have in common that they are some persons who have participated or who participate in some conference. Okay, so the idea or the principle, as I said, is ILP-ish. The language is let's say simpler or more manageable, but there is something here that is missing when compared to ILP. The concept descriptions are not in the form of, or cannot be in the form of rules, okay, with variables as we are used to it in ILP. So I was interested with my past PhD student Monika Žáková whether the taxonomies or the things, the entities native to the semantic web knowledge bases, such as taxonomies. Okay, taxonomies are the primary things, right, in ontologies. So how could they be used in ILP but still keep the expressiveness of data log for describing concepts? So the idea was that we would still induce rules in Prolog, but we would use the taxonomies provided by an ontology to guide the search in the subsumption lattice. Okay, so this orange box, that's a fact taken from the gene ontology, which tells us that the gene's function of zinc-ion binding is a subconcept of ion binding. Well, that looks quite natural. Okay. Now we try to induce rules that describe when a gene is expressed in some situation. Okay. Predict whether or not it will be expressed. And let's say we, at one point of searching in the lattice, we arrive at a candidate hypothesis that says those genes are expressed which, or whose products, bind ions. Okay. Now we see that this rule is overgeneral because it covers some non-expressed genes, for example. Okay, so we have to specialize somehow. One way to specialize would be the pure ILP way. We add a condition. Let's say the gene also interacts with some other gene called CD4. Okay, that's the normal ILP. But the new piece coming from the ontology is that we can take this concept and specialize it by replacing it with an ontology-defined subconcept. Okay, so again, the ontology, it drove or it co-defined the lattice, and we published this quite a long time ago in the machine learning, the European Machine Learning Conference. And to my pleasure, this stream of work was picked up by a guy named Anje Vaupetic, who is a PhD student of Nada Lavraj from IJS Ljubljana. And he took the idea and he expanded it and provided a general mechanism for this kind of search space structuring in an ILP system called Aleph. This is one of the very popular ILP systems, and this was just defended or presented in his PhD thesis in spring this year in Ljubljana. Well, useful as this was, this is just heuristics. This is not a theoretical framework. It's just rule of the thumb. And there is another group, or perhaps just one person, apart from these Germans, who do this ILP ontology merging. And this is in particular Francesca Lisi from Bari in Italy. And she took an ambitious adventure in which she wanted to provide a complete theoretical framework that would combine, let's say a hybrid language that would combine data log and I think OLDL, I don't know, one of these ontological languages, I don't even know which standard, because by the way, there are so many cryptic names for the ontology languages. I've seen like an abbreviation of 10 letters, and then you have a superscript, another 10 letters. Do you know what I'm talking about? Like SQH something and negation, and so this is very cryptic. But in machine learning we also have some cryptic words. Okay, I'll come to them later. Okay, back to seriously again. So this was a proposal on combining the two languages, and I'm going to illustrate it on an example that she actually used in the paper in the Theory and Practice of Logical Programming 6 years ago. So we have a database which consists of both data log stuff and ontology stuff. Okay, so we have some famous people, somebody is scientist, and then we have a rule, a data log rule, which actually is allowed to contain literals from the vocabulary of the data log part, but also from the vocabulary of the ontology. Okay, so now what's the learning test? So it's just a toy example. Okay, it's not a real-life learning test, but consider we would have examples such as Mary, of whom we know she's happy. And we could have other examples, but let's just stick to one. And then we would have the negative or counterexample, Paul. Okay, so given such examples, of course, 2 would not be enough, but in principle, given such examples, we want to induce a concept description using data log and ontology that would cover just these people such as Mary. So this is such a concept that we are actually looking for. So let's see, last night I looked at this and I worked it out, but let's see if I get it right this time. So if somebody is famous and somebody wants to marry that X, then X is definitely going to be happy. Why is that true for Mary? Well, because she's famous, so we already have this satisfied. Why do we know that somebody wants to marry her? Well, because she's also rich. She's famous, and here we use the closed world assumption. That is only in this left part, data log work. We have this closed world assumption, you don't. Huh? So we can derive that she is not a scientist because we just know that Joe is one. Okay, so since Mary is not a scientist and she's famous, she's also rich. And according now to the ontology, which I may screw up a little bit, but tell me if I'm wrong, but I'm reading the first expression as if
you are rich and unmarried, there is definitely someone who wants to marry you. Is that right? You know these languages, huh? It should be right. So from this, we can assume, because she is rich and unmarried, that somebody wants to marry her. So we are satisfying this condition. Okay, so this rule is the target rule that we wanted to learn, and we learned it. Okay, let's pretend we learned it. The good thing is, unlike ILP, we can use the ontologies. Okay, unlike the DL learner, which just learns the description logic concepts, we can have these expressive rules here. So this is called. I don't even know if she gave it a name, but you can refer to the paper in TPLP. Since I'm running out of time, I'm going to skip a technique for transforming knowledge bases into data tables which could be digested by standard machine learning algorithms. So I'm just mentioning the keyword. We call this strategy propositionalization. If you're interested, I think you can just Google it, because this work is very specific, I would say. Recently, I was thinking, couldn't propositionalization, I didn't even tell you what that is, but anyway, couldn't that be done in the semantic web standards by using not logic, but not first order logic, but description logic? And I stumbled upon a recent paper, well, not really recent, where they did something like this, something like propositionalization in the ontological world. And the reason I'm mentioning it is just to introduce this new word which I invented yesterday, and it's called ontopropositionalization. So that is the cryptic thing that we have, just like you do. Okay, I'm skipping this part, and also the kernel part. I was slower than I thought to get to what I think is the, let's say, most interesting endeavor, or one of the most interesting endeavor in the machine learning community or trying to use knowledge bases, but this time we somehow limit the notion of a knowledge base to just a knowledge graph. Okay, so that is we consider our input to be a triple store, reflecting instances of relations. Okay, so we have subject, predicate, object triples. I'm assuming this is you know this by heart. Right? This must be very native to you. Now this can be expressed as a knowledge graph with labeled edges, in which vertices correspond to named entities, and the edges, the labels, are the relations. And now some statistical people came around. I'm a logical person, but some statistical people, and there are more of them, they came around wanting to learn from such knowledge bases. And from the point of view of a logician, this looks like, how can you do it with statistics? You have a graph. Well, they found out a way, they worked out a way. So they encode this whole gigantic knowledge graph into what they call a tensor. It's like a matrix, but it has more dimensions. And in particular, we have now 3 dimensions, so it's like a cube, which has binary values in it. So what does it mean? So we have 3 coordinates, and the 2 are for individual entities, j and I, and the k, and the third coordinate captures the individual relations. Okay, so if you take a slice along the k coordinate, one slice, so it would be a binary matrix, which would capture one relation. As you have multiple relations, you have a tensor. Okay, so that's the basic structure. Now they have a binary tensor. Well, that's already something that, why is binary? So there is a 1 if the relation holds, or 0 if it doesn't, obviously. Okay, So if 0 is for all the facts that we don't have in the triple star. So usually this answer will be very sparse. And there are, of course, problems where the 0 means we don't know, or 0 means it's not true, but that is to be left aside now. So what do the statisticians do with this tensor? So imagine I want to develop a statistical model for this tensor. So I want to basically have an equation or some kind of structure that would predict the zeros or ones in the individual cells. So let's start with this model. I mean, this is not something that was derived. This is a proposal, how a model could look like. So they propose in this RESCO model that the estimate of the 0 or 1, which is this FAIJK, okay, would be obtained by this model by a matrix weighted interaction of two vectors for I and j. But what are those two vectors? So the whole idea is that each entity would be represented by a real vector, okay? But not a priori, but you would learn how to represent an entity by the vector, so that if you jointly with that learning, you also learn this weighting matrix, it would give you the correct zeros or ones as in the training data. So you're jointly learning what real vectors you would assign to individual instances and how you're going to weigh the interactions between the vector descriptions. Is that clear? This doesn't look like something reasonable. I mean, so why would an instance be represented as a vector? Well, there are at least two reasons. One reason is that this equation actually defines in a coordinate-wise way what's known as tensor factorization. Okay, so there are algorithms that actually can decompose this Y matrix into three tensors like this, and this whole decomposition is given by this simple tensor manipulation. And if you rewrite it coordinate-wise, you get exactly what we had here. So one reason for this statistical model is that it can be computed straightforwardly. The other reason is if you optimize all these parameters such that you get a good approximation of the original Y matrix, it becomes the case that similar vectors have similar semantics. So persons, among the entities, end up with very similar vectors. Cars end up with other similar vectors. And that's a byproduct of vector embedding, which is relevant not only for this single learning task, because if you do it for a gigantic database and you get such reasonable vector representations of the instances, you can use them for machine learning or even other statistical experiments beyond this. So it is really good to have a sensible or semantic-based real vector representations of entities. And there was a nice continuation of this idea, which was published in KDD 2014 by Google people who implemented in their concept called Knowledge Vault, Google Knowledge Vault, a similar probabilistic model for tensors, except without the tensor algebra. What they did was make it closer to neural learning, like neural networks, deep learning, that's the keyword of today. So they instead proposed that the Yijk would be also estimated by the vector embeddings of the instances at I and j, but they also decided to produce a vector embedding of the relations. Okay, so each of the three things, entity, entity, and the relation, they are represented as vectors. Okay, so the triple that you want to estimate the f value for, you translate it into these three vectors, which you don't know yet because they are to be learned. And now the interactions of these vectors are produced in this structure. We have a vector here that carries the weights here. And then this is then aggregated into by the squashing function, as usual in neural network learning, using again some weights to be learned into the final prediction. So it's better to look at this instead of as equations in the network materialization, so to say. So what happens is that on the input side, you have the vectors corresponding to the two entities and the relation. Okay, these are the embeddings, which go through this network as by this equation to produce the predicted value. Okay, now you may be asking, so where do I get these vectors? On my input, I have the triple store, so I don't know the embeddings. Well, the point is that the embeddings are actually learned in this network, but you have to imagine there is another input layer, like sub-input layer, which is just, I just painted, drew two entities, okay? Here they are encoded in the one-hot scheme. So if we're talking about entity number k, only the kth neuron would be 1 and the others would be 0. Okay, and then there are weights, there are connections to these vector-carrying neurons, and actually the network can be arranged in such a way that if you propagate the error, I hope you know the concept of backpropagation. That's how networks are trained. So if you propagate errors and you modify these weights, they will actually end up being the definitions of the embedding, right? Because what appears here will be actually the weights here, because this is 1. So by training this network, you obtain the probabilistic model, including the vector embeddings. And this is going to be my last slide. I'm sorry for taking too much time. So again, running it on a large triple store, the Google people found out that these embeddings turn to be, again, capturing some semantics, because not only the entities of similar semantics were similar in the vector space, close in the vector space. This is something that we saw before, right? But here also the relations, similar relations had similar representations. So a relation children, somebody's children or somebody has this many children, I don't know, had a similar vector as parents, spouse, and birthplace. So indeed, the encoding of the relation captures the semantics. So, okay, I have time for one last sentence. So this is the state of the art now. Okay, this is KDD 2014. What we are still missing, and I think the important functionality that we still do not have in the statistical work, is how to embed non-ground knowledge. So all of these fantastic things, and I was really amazed. I have some reservations, when they do not when they do not use logic, but I was still amazed. But one thing that I was not happy about is that all of this is encoding of ground instances of relations. If there are rules with variables, I wonder how that can be done. I think that's a big challenge for the next generation of researchers to tackle the semantic web and machine learning intersection. Thank you.
Thank you very much. So any questions? We have time for 2 quick questions.
Go ahead.
Fascinating. But how can I, without training in machine learning, without doing a 2-year course in machine learning, how can I bring these concepts to my semantic web work?
So I think the field needs exactly people like you nowadays, because these works, I have never seen that the learning papers from semantic web data or knowledge bases would be produced by semantic web people. All I saw was that machine learners try to somehow understand these knowledge bases and use it in tensors and so on. But I have yet to see somebody starting from the semantic web foundations and proposing learning schemes. So please go ahead.
Okay. Any more questions? So I have one. It is a bit aside from what Filip said. I basically understood the point and I see the edge that you just mentioned. I would like to mention one more thing that Axel Polares told us in the first day, and it's basically the modeling of, let's say, semantic modeling or ontological descriptions of the results of machine learning as another next topic that might be interesting. It's just my question to you, what do you think about this?
Yes, this is a big thing which I deliberately decided to leave out of this presentation because it would be too long. But there is a whole bunch of papers and projects in which they try to use learning, ontologies not as a source of data or knowledge to learn from, but to describe something about machine learning. So it's, you could say, a meta-level use of ontologies. So there was a large project in which they developed, it was called E-LICO, in which they developed a machine learning ontology of, an ontology of machine learning algorithms. Besides this project, Monika Žáková, my former PhD student, did a dissertation thesis where she also had an ontology of learning algorithms, allowing to plan workflows for learning processes. So, for example, the ontologies would define algorithms that can produce decision trees or so. So if the user wants a decision tree, by this reason, she knows what algorithms to employ. And in a similar fashion, you could think of ontologies that would capture the results so that would allow for better retrieval and search. And that is also in the scope of quite energetic research, but that was not in the scope of my talk.
Okay, thanks. Okay, and what immediately follows is the next session on knowledge extraction. I would kindly... is the data management. Right, I'm sorry for that. And I would kindly ask Ricardo Uzbek to chair this session, if possible.
No, you think it should work? Okay, let's try. Okay, so the first speakers will actually be 2 speakers. It's going to be Hussein and Mateusz, I guess. And they're going to talk about ethnicity-sensitive author disambiguation using semi-supervised learning. And I'm especially eager to see how your millions of crowdsourced annotations will look like and how you use them. Please go ahead.
Thank you. Good morning. My name is Hussein and my colleague Mateusz. We are a group of 4.
Eamonn.
When we conduct this research, we were working at CERN, which is the European Organization for Nuclear Research. Currently, I'm a PhD student in Lyon University. I'm my colleague in the University of Warsaw.
But I'm a master's student.
Yeah. So, the topic of today might be kind of vague or long title. So I decided to maybe we play an exercise together so that we understand what's the problem. Okay? Here are 2 papers, and we can see the metadata of it, like the title, we have a list of authors, the date, the venue, and so on. And in these 2 papers, we have this author, Johnson, and this author, Johnson. And we are wondering if these authors with this name are the same person or not. So I give the question to you. What do you think? Reading the title, the topic. Who would guess? Are they the same person or not? Same? They are not.
So as far as I remember, one of the person was Randy Allen Johnson and the other was Robert Adam Johnson or something like this.
So 1 vote for you, -1. Okay, another one. What about this? You have this author. I think it's a Russian name. So it's maybe. And this one, you can see that they're written differently. Here, there's a variation. Here is like shin. They came the date. What do you think? Same? Because, yeah, they're the same. So, this is kind of problem that we are facing at CERN, Digital Library, and we try to solve. So, I hope that was a good. But even more problematic than other Western or Russian names, Asian names. Sometimes we find this, like 3 real authors, Yang Guang, Yang Guang, Yang Guang, the same way. When you write it in the Western letters, it's like this. So it's even more problematic. So this is not something very special. This could be categorized into another topic called entity resolution, in which, for example, yesterday we heard a paper about that, when you try to find duplicates in database about hotels. So in real world, we might have like two instances, 2 objects, but in the database, you might mention them differently. So you have duplicates. So in a way of make data quality or to enhance, enrich your metadata, sometimes you face this problem, and author disambiguation is part of that as well. So it could be applied in many applications. So this is the problem we have. So to solve that, I want to introduce a term to you, which we call signature. So what is the signature? We have a group of publications. In each application, we have a list of authors. An instance of publication and a single author. So we take an author, a publication he wrote, all the metadata about this paper. This is what we'll call a signature. And we will use this concept to solve the problem. So a paper with like 10 authors would have 10 signatures. Okay? So the problem we want to solve when we were working at CERN, we have a digital library called InspireHib. It's a digital library of high energy physics. It has over 1 million publications. It forms more than 10 million signatures. So the good thing we have, what we also have to solve, we have about 12% of this data are actually like ground truth. They are actually solved. So these signatures are for this author, these are for this author, so we know, even with this variation, we know who wrote what, which is important when you make accreditation to the researcher and so on. So how we did this, sometimes we take it from the authors themselves, like Google Scholar, you can have a profile, so you can group what you wrote, so it can, somehow you know who wrote what. So we have, in Inspire Hub, we have something like this. There is a universal identifiers recently going on. You try to have a unique ID for you as a researcher or author, and you use this ORCID ID when you write or publish a new thing. Or you can hire a curator, which is expensive, and we had that at CERN, like the curator for yesterday when we tried to disambiguate hotels, which is also very costly. So this is what we have, and we are not very happy with that, so we try to do something could be smarter. So what's the problem? If we look at it as in a machine learning point of view, we have a set of signatures, like author and what he published, and we will try to build a model such that we group signatures that corresponds to a real author, even if you have here a variation of the name. Or maybe these two signatures have exactly the same name, how it's written, but actually there are two authors. So this is the problem that we want to solve. This is how we formulate it. So manual curation is costly, as we said. So what we can do? What we did, thinking of machine learning solution, is similar to what had been discussed yesterday. Take two signatures. Are they the same author or not? If they belong to the same author from the ground truth we have, if we know that's from curator or from a profile, we vote 0. And if they are not, it's 1. And we can build or learn a binary classifier, which is a typical supervised learning in machine learning. So this is what we call supervised learning. You have a set, you can generate a lot of pairs. You have a lot of 10 million signatures, randomly generate pairs, and try to, for each one from the ground truth, are they the same or not? Are they the same or not? And then learn this model. This model might be able to infer that if these giving two authors, are they the same or not? So this can help. So we start with that. To feed in a supervised learner, you need a set of features. Okay, you need, for example, are they from the same affiliation or not? Which year they published? What's the topic they published on? So from this feature, you can actually, as a curator, you can see if they are the same or not. But since we had in mind a problem of Asian names, which is more problematic, actually, we tried thinking to build first a set of features that represents the ethnicity from the name. To do that, we need a data set, which was not available. So we had to build such a thing. It's very sensitive information, as you can guess. From a name, what's the ethnicity, the race, so it's kind of sensitive. So, but we managed to have a limited access to such a data set from APUMS USA. So we can have like 20 million names, white, labeled as white race, 3 million black, and so on. We have this data set. And we sample from each race class, we have 7 classes, 50,000 names. And we give it to, we process these names by getting 5-to-1 Ngram range and apply TF-IDF, like typical text mining feature extraction. And we use an SVM classifier, one versus all, to predict, giving a name, how probably he or she will be like white, maybe 50% black, 1% Asian, and so on. And we want to see if this can help or not in the problem. So, this might be a bit scary, but I will kind of end of it. Giving 2 signatures, how we can get what we call pairwise features. Because giving 2 signatures, are they the same or not? For example, if we get the title or the the author name itself. We can vectorize it in a way, like TF-IDF, and then we combine both two. For example, if it's two vectors, we can combine it with the cosine similarity. And this information, like the publication title, could have one feature. For ethnicity, we actually generate 7 features, because one feature per each ethnicity, which represents how probably this name would be, for example, white or Asian, and so on. So we create our data set. We have sets of features, about 20 features, and we want to predict are they the same or not. This is the list of features we have. Starting from the full name, we can apply any gram of 2 to 4 with TF-IDF, and we combine these two signatures by a cosine similarity. Sometimes we use absolute difference, what's the period between the two publications, and so on. And also we have the ethnicity features. Okay, so we are happy with that. We learned something, and we will see what's the most important, how we can evaluate these features list. Not all of them are as much important as we can think. For example, we found that if we start removing one by one feature, how that will affect the F measure on the test set. And this is the results we have. And this shows us that ethnicity features that we came up with is actually something novel we introduced in this work, actually has a high contribution, as well as co-authorships from the metadata, the affiliation, and so on. So this is what we found. So again, our problem is having signatures, disambiguate them into this. So we are not there yet. We learned like a linkage function, what we can do, how we can do this thing. In machine learning, we see it as a clustering problem. So imagine here that we have in the bottom we have signatures, and based on distances, we try to group these signatures together. For example, we can cut here, we say this is an author, this is an author, this is an author. How we can measure distances? The linkage function we learned, which is the classifier, that can say it's the same author or not. We take it as a probability. How probable these two names would be this for this author? It's a value between 0 and 1. And this value we use as a distance function, or a dissimilarity. And this is we use in this hierarchical clustering. And if we can come up with like 3 clustered up with that, this set of authors are actually 3 persons. But if you have 1 million signatures, if you apply hierarchical clustering, it's an NP problem. It's not visible in normal memory. So we have to solve this problem. Another problem in this solution is where to cut. If I cut here, we have 2 authors. If I cut here, we have like 10 authors. If I cut here, we have 3 groups. So where to cut? And these problems will be addressed with my colleague Mateusz, and when he will describe the whole pipeline that we did. So the first solution is to make a blocking. We divide the problem, and we use a way to cut. And after we did that, we will find like our solution. For each group is the real author. So I will give the stage to Mateusz to describe that.
Thank you, Hussein. Okay, so the first problem that we need to solve is reducing the complexity time of our algorithm. Like Hussein said, the algorithm has n-square complexity. So what we need to do, we need to take all the signatures and partition them into blocks. This concept was previously in this domain called blocking, and thus we will stick to this name. So what we need to take care of while we partition this domain is partition all the signatures, is that firstly we need to create as small blocks as possible so that the sum of the sizes of the squares that you can see here on these examples is the smallest possible, then our algorithm will be the fastest. And we need also to take care of the fact that every pair of signatures belonging to the same author should be within the same block. Now here we have a small example. So those are some kind of names. Let's say that those are signatures written by Abe, Catholi, Effie, George, Jack, and Natasha. And if we wanted to do our hierarchical clustering without any blocking, we would have to do all those computations for every pair of signatures. And with blocking, if we, for example, block those signatures about the name as it appears on the paper, we need only to compute those green squares. So here maybe the difference between computing all of them and only the squares is not that big, but think what happens if we have more than 1 million of signatures. And if we need to compute only the diagonal, then the computation is much faster. One can think that it's more or less like linear. Okay, so the most commonly used approach in the past is what we call surname and first initial blocking. So it means that if somebody has a signature, he takes the surname of the author and the first initial, so the initial of the first given name. And after taking all of the signatures with the same surname and the first initial, we group them together. However, there are some limitations of this technique. So unfortunately, there are some cases where the signatures will not belong to the same block. We analyzed our training data and we tried to find those cases, and we grouped them into 5, let's say, groups. And the first one that we noticed was that sometimes the surname is not written in the same way. So for example, here we have a very common German name Miller, usually written with an umlaut letter, so this U with 2 dots on top of this. I believe that the standard way of writing down this name, if you don't have the umlaut letter available, is writing it with UE, but unfortunately some publishers simply write it down as Muller. So then if we use the surname and first initial technique, we will have those signatures unfortunately blocked into different blocks. The other case were multiple surnames. So for example, in Spain a lot of people have 2 surnames and so on. And often some of the publishers simply use the last family name as the only surname. The other case was where the publishers used only the first family name as the surname. There was also a case where we found signatures with multiple given names, but sometimes the first one was not used. We don't know why, but it happens. And there is unfortunately also the case where the surname changes completely. So for example, a marriage can be the case. Also, I need to mention that in this first group, we put all of the problems with transliteration. So for example, I don't know if you remember, but there was this example of Mr. Vaniashin, the one where we asked you whether it's the same author or not. It's basically a transliteration problem. So his surname is written in 2 different ways, but it's the same author. So we propose our own solution for blocking to improve that. What we do is we take all of the signatures, and then we take all of the signatures with a single family name, and we group them by phonetic representations. What does it mean? So basically, there is such concept called a phonetic algorithm, which is basically a function from a word to its phonetic representation. An example of those algorithms is NYSIIS, sound Excel double metaphone. I don't know if you are familiar with that, but they work quite well. Then what we do is we cluster then if we have those groups ready, we take also all the signatures with more than one family name, and we check whether the phonetic representations of the last family name exist in those groups. If yes, what's more is not on the slide. We also check whether the last given name matches the first surname. So here we had, for example, Martinez-Torres example. So we are checking whether the Torres block exists. If yes, we also check whether Martinez is somewhere there within the given names. If yes, we add the signature to this cluster. Otherwise, we check the other given name. And we add the signature to the other cluster. If both of them don't exist, we create a new cluster. So this effectively solves first 3 of the cases. This one is very hard to handle. This is something that we didn't work on. I mean, Basically, we would have it solved, but unfortunately, after doing this, we need also to split our clusters over the first initial, because the resulting clusters were too big to handle still. So we have the first problem solved. Now what we do with the second problem? So the point is that we need to decide where to cut our dendrograms, the ones that Hussein introduced. We tried 3 different techniques. So the first technique is simply to say that, okay, we have a dendrogram for every block because we ran our clustering algorithm for every block separately, and we simply don't cut at all. We say that clustering is not needed. We simply say that block is enough, and we think that this is a single cluster, this is a single cluster, this is a single cluster, nothing more than that. Other approach that we tried was cutting globally, so we simply decide on globally on a height where we should cut our dendrograms. And the other approach were block cuts, so we choose a different level for each of the trees. Now, how we choose those 2 levels? So what we did is we did it in a semi-supervised way. We checked all the possible heights, and we simply evaluated our solution after check on the training data for each of the heights. Now, how the evaluation works, I will explain later. Actually, I will explain now. So the point is that we need to evaluate the clustering step. It's not that easy. There are 2 very popular ways of evaluating clustering in machine learning when you have some training data available. One of them is called B-cubed, the other is called paired F-score, which we used both of them on the paper, but here we decided to show only this one as we believe it's better for our problem, as it tries to balance, it does not take into account, how to say that? It tries to, it works very well for problems where the clusters have different sizes. Which is actually our case because there are authors who have written a lot of papers and there are authors who have written like 2 or 3 papers and so on. So we use our claimed signatures. There will be around 1 million of them. We form the ground truth clusters. We split them into a training and test set. We use also cross-validation for that. Here are the definitions of the B-cube scores. I will not dig into details. And then we computed our results using our pipeline. So what I should describe here? So first of all, I would like to say that the underlined rows are the rows that show the techniques that were used in the past in the state-of-the-art approach. So this is something that we found in the publications from recent years. And we try to show here how we improved over the state-of-the-art solution. So first of all, baseline. What is baseline? Baseline is simply a auto-disambiguation technique, which you don't do any sophisticated machine learning. You simply say that each surname and first initial, am I right? It forms a new author. So as you can see, the score is still quite nice, 0.94. But we still care about all the errors that it introduces, and it tries to minimize the number of errors. It's very important for some users because most of the cases are very simple. There is only one author who has this name, and it's not a problem to disambiguate that. But as Hussein said before, there are, for example, those Chinese authors who share the name, and then we need to work on that. Okay, so first of all, I would like to compare the blocking approaches. So what I told you that previously, the commonly used technique was surname and first initial. Here is the score for that, and we tried to improve it by using the technique that I presented with all 3 of the phonetic algorithms that I suggested. So the best one for us was NYSIIS, which improved from 0.983 to 0.985. Now, the important thing here is to mention that those approaches improve the recall score. Why is that? So basically, whenever you have a pair of signatures that belong to the same author and they are split over 2 blocks, it does not affect the precision of the algorithm, but it affects only the recall. So here we can say that actually this technique improves the recall, so that's what we wanted to do. Now we try different classifiers for learning our linkage function. The most commonly used classifiers are ensemble classifiers, and there is a good reason behind that. Because first of all, it's very easy for them to learn nonlinear dependencies. They are basically created in order to do that. And they are very good for non-heterogeneous data. For heterogeneous data. And just like in previous work, we found out that the two best classifiers is gradient boosting classifier and random forest. In our case, random forest was slightly better. Another thing that I didn't mention before is the way of choosing the training pairs. So whenever you do an auto-disambiguation, it's very important to choose the training pairs in a balanced way, only from the same block. The balanced, what do I mean by balanced, is that you try to have the same proportion of pairs with the same surname, with different surnames. And there was another case, or? No, I think that those are the cases. Okay, so I don't have much time, so I'll try to speed up a bit. Then again, we try to use different linkage functions inside our hierarchical clustering. So basically, a linkage function is a way of merging two clusters in a bottom-up approach in hierarchical clustering. The best one was the average linkage. And we also checked the cut techniques that I mentioned before. The best one was block cut, so the technique where we chose a different level of cutting within every block. And here we also wanted to show you that actually, without ethnicity features, our algorithm performs worse. So this is a very good indicator that our algorithm has this ethnicity sensitiveness built in. So those are the summary results. This is the baseline that I described before. Our model has much better score. It's also better than the state of the art, which scored 0.983 on our dataset. Now, the important part of our paper is that our implementation is first of all integrated inside the Inspire digital library at CERN, but we are also aware that there are at least 2 private companies that use our solution already. And the solution is only like 1 year old, so it seems that it's getting quite popular. The execution time is 20 hours for 10 million signatures on 60 cores machine. But the important thing to note here is that you don't have to do the full disambiguations every time you receive new signatures. You can do the disambiguation in incremental fashion. How does it work? So basically, I told you before that we have this blocking step. Wherever you have new signatures arriving, you do disambiguation only on the blocks of the new signatures. You simply say which blocks the new signatures will be put in, and you do the disambiguation only there. So it takes much less time, usually a few minutes for like 100 of new signatures. Our solution is completely open source, and it's a library not only for auto disambiguation, it can be used for any entity disambiguation task. We also decided to release the dataset as, unfortunately, in the domain of auto disambiguation, there was no good benchmark. So basically, people were writing papers and trying to compare their solutions. But without a dataset that can be used as a benchmark, one could argue that the comparisons are not perfect. Here are the links for the open source library and the dataset if you want to use them. And so finishing our presentation, there are some conclusions. First of all, we were the first ones to use the semi-supervised approach on such a big dataset. We had more than 1 million of claimed signatures. We introduced some novel blocking techniques based on phoneticization. We showed the significance of the ethnicity features. And we also showed the importance of balancing the training set. What still needs to be done? First of all, we need to do some error analysis. We are not yet sure which part of our algorithm introduced the majority of the errors. We need exactly to check why those errors are caused by, for example, linkage function step or clustering step. Moreover, we should be able to find a better name ethnicity dataset to improve our ethnicity sensitiveness. We believe that auto-embedding might be a good approach for a blocking strategy. As I told you, there is a problem that some authors change their surname completely. So we can't do much with the phoneticization techniques there because the surnames are so far away. But if we use auto-embedding, maybe somehow we can fight off this problem. We can also try to build a phonetic algorithm tailored specifically to the disambiguation task, because the ones that we used work for any possible word, and we have much less cases to handle, so perhaps it's possible to improve here. And moreover, we need still to have some user feedback. If they notice that, hey, those papers don't belong to the same author, they should tell us, and we maybe can improve our algorithm. And we should try also our disambiguation solution, so the library that I told you about for other entity disambiguation tasks. And it's the end of our presentation. I hope I didn't take too much time. Thank you. Yes, please.
Thanks a lot for the presentation, and especially for open sourcing the data set. It's really great. One thing that I'm have you actually solved the case where the surname has changed? Because you're voting on it, you will probably vote the same author in one block if the surname has changed. Well, yeah.
This is one of the future work as listed in the end, because as you see, the blocking strategy depends on the last name, phonetics. So yes, this case is not solved, but in the future work we're trying to do this work to back style of take the author name with all its features in the publication and try to see similar vectors, and based on that we form the block or the partition, which will include, for example, if for example, a research lady changed her name, but her publications are very similar, this will put her in the same block, so that when we do hierarchical clustering, we will include that. But without this, we cannot, it's not still not solved, it's a future work.
Yes, so we basically solved only the first 3 cases from this list.
Yeah. Yes?
Why not to use email for classification?
Very good question. This is the first thing we were thought of. Unfortunately, this information is not available for all authors. The percentage of that, in the recent years, they start to use this kind of identifier. Plus, authors changed their affiliations and changed their emails. So when it's available, we try to use it within the feature sets, but we found that the proportion of that is not sufficient to include it as a feature.
I got actually one. How does your algorithm cope with new authors, like new PhD students with their first publication? Is that the same problem like you mentioned?
So yes, it's the same problem, and actually I believe that it wouldn't pose a big problem because we have this hierarchical clustering approach. So basically, the new PhD students might be clustered together with some other, let's say, scientists who have the same surname, so they might actually be in the same block. But then again, we have this cutting technique here. So if there are any new PhD students, they should form new clusters because of the cuts. Obviously, there are some errors sometimes, but hopefully in the majority of cases, everything works fine.
And the pipeline is incremental, so we will not run, just take this one, put it in the middle of the pipeline, and actually this is how it works now at CERN. Yeah, when we aggregate new papers from archive or something, this is what happens.
Interesting, thank you. So let's thank the authors again.